So we talk about polygon, which is closed, broken lines. And close it. Okay, we need both. There is something called convex polygons. Convex polygons, the definition is that when you find the sides made of the polygon, if you extend any of those, the line is not go through the interior of the polygon. Like you extend this line on both sides, it's not this is the interior of the polygon. It's not going inside. Or you extend this one, it's not going inside, and this one is not inside, and this one is not inside, this one is not inside. So that's called convex. A triangle is a perfect example of convex polygon, because the sides expand that, you will never touch the interior, will never cross it. But you could have a polygon like this. Now, why do we say this is a polygon? Because it met the definition, right? When we say something is we just said as long as it meets the definition, then that has to be that thing. So this one, we see that it's closed and it's made broken lines. But this is different from this kind of polygon, because if we extend this line, I'm using a bit, if you extend this line, this part goes through the interior, or extend this line, it goes through the interior. So this is called concave polygon. Good?
Yeah.
And the one we are studying mostly is the convex polygon. Even though we can also study the concave polygons, but most time we study convex polygon. And the quadrilaterals we are studying mostly means pretty much focused on the convex polygon. So we got two definitions. And then we'll talk about something called equilateral polygon. Lateral polygon. So that basically is all the sides have the same length. Okay, so it's not, as long as all sides are equal lengths, then we call it equilateral polygons. And now with that, we can talk about quadrilaterals. Quadrilateral. So the quad here just means four, lateral just means lines. So we say a quadrilateral is a polygon, of course. It's have four sides and they are closed. So this will be quadrilateral polygon. We call this quadrilateral. Okay, it's quadrilateral. Got four sides. And of course, we could have, this is a convex. You could have concave because it could have something like this. And that is also a quadrilateral, but this is a concave. And then from there, we're going to make a definition about parallelogram. So that's where we're going to see it again, the difference between definition and properties. So definition of parallelogram, first of all, is a quadrilateral. That means they got four sides. And second of all, that is the opposite sides are parallel. That's the name we came with, parallelogram. A gram just means graph, parallelogram. That means if you have something like here, this side and that side are parallel, and this side and that side, they're called opposite side. So they're opposite each other. So opposite sides are parallel. parallel. Then we call that parallelogram. And one of the things in our modern terminology that we could say a parallelogram is a quadrilateral, and AB is parallel, use that, CD, and AC is parallel to BD. So that's basically that's our definition. Okay. Good?
Yep.
So that's that parallelogram. And then we're going to look into properties of parallelogram. This gives us to the proposition 21. Yeah. Okay. So we can we'll skip some propositions, so you can just focus on that which are kind of essential to what we study of the geometry. So this proposition said that if you have a parallelogram, which means you have to meet all the definitions, and when you're trying to prove something, then you have to go back based on your definition. So we have a parallelogram, so that's given. Parallelogram. And and we're saying that if you divide the parallelogram, so either you go from connect AC, then you get two congruent triangles. So you also have ABC is congruent to triangle ADC. Good?
Yep.
ABC, okay. All right. And that's the proposition. So because the proposition, we need to prove it. And how do we prove that? Remember, in order to prove triangle congruency, we have either side, 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 or side, angle, side, or angle, side, angle. And so that's the three main things we need to prove. Of course, we also have angle, angle, side. But those are three are the main ones. Okay, so how do we do that? Now, what we see that because BC is parallel to AD, so that's given because by the definition, a parallelogram is that. And then we'll know this angle and that angle are congruent. So if we put this as 1, and this is 2, and that angle 1 is congruent to angle 2. So that's based on the properties of parallel lines. So that's what we learned before. When you have two parallel lines, the transversal, right? You got those alternate interior angles are congruent to each other. Okay, so we have that. This is one angle. And we'll know that AC is congruent to itself because that's the same line, right? So that's one side. We need just one more angle, angle, side, angle. And we all notice that this angle, which is 3, and that angle 4 are congruent because this line and that line are parallel. So 3 and 4 are congruent. So therefore, ABC is congruent to triangle ADC. Good?
Yep.
We got angle, side, angle. So now we prove a property of a parallelogram. So the property is, if you have a parallelogram and you can cut them to two congruent triangles. So it doesn't matter you cut this way or cut that way. You're going to have exactly equivalent two triangles. Okay.
Yep.
So now we're going to move on to the next one. So now we're talking about, when we say the properties, and basically we're talking about the properties of a parallelogram. So we say proposition 22, and said that what's given is a parallelogram. And we got a parallelogram. And we got AB and CD. So this proposition say that is, if you draw a diagonal, so B to D, that's a diagonal, and A to C, you're going to cross at point in the interior. Let's say this cross side is E. So when you do this, then this line is a bisector of this line. And also this line is a bisector of that line. So basically what I'm saying, BE is equivalent to BE and ED. So this and that are congruent. And also AE is congruent to EC. And this and that are congruent. So basically, BD bisect, that's bisect means cut them to equal half, bisect AC. So one diagonal cut bisect the other, and also AC bisect BD. Good?
Yep.
So how do we prove this? Okay. And we're going to play the same game of finding the triangle equivalency. So basically what we're going to prove is that this triangle are congruent to this triangle. Good?
Yep.
Then therefore, because they are congruent triangles, then this side and that side will be congruent, and this side and that side will be congruent. So how we go about that? Well, let's see. We know this angle and that angle are congruent, right? Good.
Yep.
We know this angle and that angle are congruent. So 3 and 4 are congruent. So we know two angles already. Now we just need to prove one side. And what we're going to prove, we're going to use the previous theorems, prove something we proved. Remember what we proved before is that ADC, that triangle is congruent to ABC, right?
Yep.
We just proved that, which means AD has to be congruent to BC, right?
Yes.
So that's a property of the equivalent triangle, is that the sides has to be the same length, or we say congruent. So now we have this angle corresponding to that angle congruent, and we got, trying to say different color, we got this angle are congruent to this angle. We just use this to see the congruency. And we now also know, I'm trying to, let me see, use the card. Now we know this side is congruent to this side. So what theorem we're going to use? Angle, side angle, right? We good on that?
Yeah.
Angle, angle, side. So therefore, we know this triangle BEC is congruent to the triangle of BEC is to be the DEA. Okay.
Yep.
So as a property of congruent triangles, then all the corresponding side has to be the same. That means BE is equal to ED and AE is congruent to EC. So therefore we prove this proposition. Good?
Yep.
So kind of recap here. We got a parallelogram that's given. So if it's given, it does meet the definition. And because it's a parallelogram, so therefore we have this property that the diagonals are bisect each other. Good?
Yep.
All right. So that's what we have for today. I'll see you next week. Okay.
Thank you.
You're welcome. Bye.
Bye.
Bye.